Hi, my name is Caroline Means, and this is Lab 5 on the subject of Faraday's Law and magnetic braking. The goal of this lab is to collect some basic data about a conductive tube of aluminum foil and the time it takes a bar magnet to fall through said tube, then to use this data to computationally model the movement of the magnet investigating Faraday's Law with the help of Newton's laws of motion. After completing the experiment, I found that it took 1.264 seconds for the magnet to fall through the conductive tube experimentally, and when I modeled this, it took 1.04 seconds for the magnet to exit the tube. After completing the experiment, the first step I took for this lab was to collect all of the equations I would need to translate into Python to create the computational model. You can see on this slide the equations I used to calculate magnetic field, the flux created by the magnet in motion, the gravitational force, the magnetic force acting on the ring, and the velocity and position update formulas. All of these formulas were used to step through the process of modeling the motion of the magnet. First, the code establishes constants and known values, and then it builds visual representations of the magnet and the tube. It then uses a function from Lab 3 to calculate the magnetic field of the bar magnet. The next function used calculates magnetic flux from a specified magnet moving in relation to a segment of the tube, modeled as a ring. The tube overall was modeled as lots of consecutive rings, with the more rings increasing accuracy. With this information, an iterative loop begins by calculating the current time, the gravitational force acting on the magnet, the magnetic force on a specific ring due to the magnet, then the net force acting on the magnet, which is finally used to update the magnet's velocity and position. This process is repeated for each of the rings which comprise the conductive tube of aluminum foil. The result of all of these series of calculations is an animation representing the movement of the magnet through the tube. This is produced along with a graph of the magnet's velocity over time. As previously mentioned, there is a discrepancy of about 0.2 of a second between the calculated and experimental times. These discrepancies are most likely due to the fact that the calculated magnetic dipole value from Lab 3 is used in the code for this calculation, in addition to a potentially imprecise weight. Nonetheless, the two times are very close, and thus we can see how a changing B field induces a force opposing the motion, in this case, causing the magnet to slow down. If the resistivity were to go to 0, the time spent in the tube would decrease and become more linear. As resistance decreases, current increases, so the force exerted on the magnet at that speed is larger than it would be for a bigger resistance. If holes or slits were cut into the tube, it would less effectively slow down the magnet, as the field created would be inconsistent. This is very similar to what happens when there is more space between the rings of the model or less rings. Overall, this lab did a great job of demonstrating the effects of a magnet in motion.